Hi, this is Paul from All About Digital. This is Chapter 3, Part 3 of Karnaugh Maps. And in this video, we're going to continue to do examples of Boolean expression reductions using Karnaugh Maps, different types of Karnaugh Maps, 3, 4, and 5 variable Karnaugh Maps, and we'll introduce some new concepts like don't cares. So please like the video, subscribe, list any comments below, and enjoy the video. Thanks for watching. In this video, we're going to continue to use Karnaugh Maps to reduce and optimize Boolean expressions. Many reduction examples will be solved using common mapping techniques. And then we're also going to introduce the concept of don't cares. Well, let's start with a POS example where we're going to map the zeros of a function and generate the product of sum terms for those zeros. This is the Karnaugh map. And in this map, we've mapped all the zeros of the function. Okay, and those are the zeros here, 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 here. Okay, all the zeros are mapped in the function here. Okay, so looking at this map, we can see that there's no 4 covering anywhere. There's no 4 together. So the largest covering we're going to be able to do is a 2 subcube. So let's just start by covering some 2 subcubes. There's one right there. There's one right there. There's one right there. So that looks like all we can do with the 2 subcube coverings. The last one's just going to be a covering just in a single cube. So let's write down the sum terms for these coverings. Remember that when we write down the variables, whenever the variable is a 1, we complement it, and whenever it's a 0, we use the uncomplemented form. So this first covering is a W bar, because there's a 1, W is a 1, plus X bar, plus Z changes from a 0 to a 1, so it drops out, and we're left with a Y of a 0. But for the zeros of the function, that's equal to an uncomplemented variable. Okay, let's do the second one. That's equal to W plus X bar, because W is a 0 and X is a 1, plus we have in this covering right here, we have Y changes from a 0 to a 1 and the Z is a 1. So that's going to be equal to Z bar. Okay, let's do the third one here. Third one, the X changes from, the W changes from a 0 to a 1, so we're left with a 1 for X, so that makes it an X bar. And then we have Y is a 1 and Z is a 0, so that's equal to Y bar plus Z. Okay, so those, oh, I'm sorry, there's one more. Those are the 2 coverings. That's what I meant to say. Okay, the last one here, no variables are going to drop out because we're covering a single cube. So W is a 1, so we have W bar. X is a 0, so we have X. Y and Z are both 1, so we have Y bar plus Z bar. Okay, in this slide we show that this is the POS representation, and I've kind of color-coded, I have color-coded the same coverings that we made before and wrote down the subcubes associated with these 4 coverings, and shows that the final solution is the product of each of these sum terms, S1 through S4, and then this is the final answer for this particular example. Okay, now we're going to talk about something called essential subcubes. So how do we know we have a minimal solution? And then, in fact, how do we know if we have a unique minimal solution? Well, unique meaning that's the only minimal solution that there is. Well, we can say that if we're going to introduce the concept of essential subcubes, which says that there's only one way you can cover certain ones in the map. And if that is the only way you can cover all the ones in the map, then you only have essential subcubes, and therefore it's a unique minimal solution. So let's talk about that a little bit. Let's look at this map right here of the ones from this truth table. We can see that the red ones that I've outlined here, there's 4 of them. There's only one way to cover these red ones. This one can only be covered with the one adjacent to it, like this. This red one right here, let me remove that, can only be covered with this one right here. This red one right here is only adjacent to that one, so it can only be covered by this one. And this red one can only be covered with this red one up here, which it is adjacent to. So all of these cubes, all of these subcubes can only be covered one way. And if that's true in a covering, then these are called essential subcubes. Each one of these is an essential subcube because it can only be covered one way. And if every subcube in your map is an essential subcube, then this is a unique minimal solution. Unique, which means there's only one minimal solution. Okay. So again, I've color-coded it and showed that for that same map with the essential subcubes, the final solution is the function is equal to wy bar z plus wxz plus wy bar z bar plus w bar x z bar. And that is a unique minimal solution. There is no other minimal solution for this function. Okay, not every covering, in fact, probably the predominant number of functions will not have all essential subcubes. More than likely, it'll be something like this, where we have a 1 here and we have a 1 here that we didn't cover. Well, when you're covering ones on a map, you would like to not isolate any ones. In this particular covering that I'm showing here, we've isolated these 2 ones. So this is a poor choice because the only way to cover them now is to cover them this cube and then this cube right here. And it's a poor choice because we had to use 5 subcubes to cover the ones. 1, 2, 3, 4, 5. And that's because we isolated those 2 ones. Well, let's look at a better way. Here's that same map, and there's 2 different ways to cover it. For this function right here, you can cover it this way. Okay. And notice that for this covering, there's only 1, 2, 3, 4 subcubes. The previous one had 5. So this is a better covering. Well, you could also cover it this way. You have 1, 2, 3, 4 coverings for this particular, the same map. So this one is no more minimal than this one. They're both minimal, but they're not unique. And either one of these 2 is correct. So there's 2 ways to cover it. There's 2 minimal solutions, but there's not a unique minimal solution because you didn't cover it with essential subcubes and there were no essential subcubes. Okay, and this is a repeat of what we just talked about here. And again, either one of these solutions is acceptable. They're a little bit different, but they have the same number of terms and the same number of variables in each term. All right, Let's look at K-map orientation. And what do I mean by that? Well, we have a truth table, and the truth table typically is always the same. We have the inputs, A, B, C, and it has all the combinations from 0 to 111 for this particular case. And then here's the function. Well, we can write a Karnaugh map like this first one here. We can put variables A and B to the left and variable C on the right. So this is what the Karnaugh map would look like. Also, we could draw the Karnaugh map where we have an A to the right and then the B and C on the left. So we have the ones of the function, the output ones as a function of the inputs A, B, and C. You can see that the orientation is different between the two. And actually in this three variable map, you can have a third orientation where you have an A and then a B, C. So the A goes from 0 to 1 over here, and then this makes it a horizontal map. Well, are these identical? Is there any difference between these three? Does it make a difference how you draw your K-map? Well, let's check it out and see. Let's do an example. Let's look at this one. The function for this one, it's a 4 covering. C changes so it drops out, and B changes so it drops out. So this function is equal to an A. Let's do it for this second function here, the second K-map, second layout. This function, pretty easy, is an A. B and C change from top to bottom. So this function is also equal to an A. So it's the same as this first map. Let's look at the third map. Let's do this covering right here, all the ones. So in this case, the function is equal to, again, just A, because B and C change and A doesn't. So it's A. So these are all the same. So bottom line is, for this 3 variable map, it doesn't matter how you orient the A, B, and C. In fact, some people will talk about it one way, and some people will talk about it another way. Some people will they'll lay it out either one of these 3 different ways, and they're all correct. So it doesn't make any difference. Let's look at a 4 variable map. Here's an example of a 4 variable map. Okay, there's 2 4 variable maps. The first one, we have the WX up here, and then the YZ down here. And this one, we have the WX right here and the YZ up here. Okay, let's map both of these, reduce the function, and then compare the result. For this one, here's the first covering, and we'll do the second covering right here. There's the second covering. Okay, so the function of this is equal to W changes, so we're left with X, and Z changes from 0 to 1, so we're left with Y bar, plus the 2 covering. X changes from a 1 to a 0, so we're left with W, and Y bar, Z bar. Okay, that's for this orientation of the K-map. Let's look at this orientation, the second orientation. Well, let's do our coverings. There's a 4 covering. And there's a 2 covering right here. Let's write down the function. Function is equal to, this covering right here is X, because W drops out, and Y bar, because Z changes from a 0 to a 1. X, Y bar, plus this is equal to W, because X changed from a 1 to a 0, W, and then this whole column, it's Y bar, Z bar. And again, what we see is these 2 functions are the same. So again, it doesn't make any difference how you orient the variables, the external variables in your map. You just have to lay the map out like 0, 1, 3, 2, 0, 1, 3, 2, but you can you can move the variables around. You just hit, and the ones will appear in different subcubes, but the adjacency will be maintained. So it doesn't matter which way you do it. All right, now we're going to compare, do a little exercise here. We're going to reduce a function with Boolean algebra, and then we're going to reduce that same function with Karnaugh Maps and see what the difference is. See the amount of work that we have to do. Okay, so let's do put the ones in the Karnaugh map. So this is 0, 0, 0. We have a 1 right here. There's a 1. 0, 1, 0, 0, 1, 0. We have a 1 right here. And then 1, 1, 0. 1, 1, 0. We have a 1. I'm sorry, 1, 1, 0. Okay, we have a 1 right there. Okay, 1, 1, 1, 0. Okay, so let's use Boolean algebra to reduce this. So we're going to take the three standard product terms, as we discussed earlier, and it's going to be equal to, this first one is a bar, b bar, c bar, plus a bar, b, c bar, plus a, b, c bar. Okay, we're going to use Boolean algebra to reduce this. So this is equal to, we're going to factor out a bar, c bar of the first two terms here. So we'll take out an a bar, c bar, and what are we left with? B bar plus b plus ab c bar. Now, look at b bar plus b. Anything plus its complement is equal to 1. So according to Rule 8, this is a 1, and it's equal to a bar c bar plus a b c bar. So this is, we're going to take out a c bar, factor out a c bar out of there, and we're going to get a bar plus ab. I'm sorry, this is a c bar we factored out, okay. So this looks familiar. Well, let's look at number 11 right here. This says if you have the variable plus its complement times another variable, it's just equal to that variable plus that other variable. Well, we have x plus xy, x plus x bar y. Well, here we have a bar, that's the variable, and the complement of a bar is a. So that's just equal to a bar plus b, according to Rule 11. Okay, so it's equal to c bar times a bar plus b, according to this Rule 11 right here. And that's equal to a bar, c bar, a bar, c bar, plus b, c bar. Okay, that's our final answer. Let's go up and map this with Karnaugh Maps, with a Karnaugh map, using Karnaugh Maps. Okay, we'll map it in black here. So we have, looks like we have two coverings. There's one covering there, and then there's a second covering right there. Okay, let's just write down what this function is. The first one is a bar. Function is equal to a bar. And then what changed from here to here? What changed from there to there was the b, so we're left with c bar. A bar, c bar. Okay, that's a bar, c bar, plus this function here, the a changed from 0 to 1, so a drops out, and we're left with b, c bar. B, c bar. Well, that's exactly the same as this one down here. A bar, c bar, plus b, c bar. Quite a bit easier with the Karnaugh Maps. So that was just a demonstration. You can practice this for yourself and do the same thing. Minimize using Boolean algebra with all the the min-term representations for the ones, and then use the Karnaugh map, and you'll see just how much easier it is, as we demonstrated. Okay, here's a 3-variable map. Let's do a minimization here. There's one subcube. And there's the other subcube. So what is this function equal to? This one? This one is equal to A and B change all the way down, and just equal to C bar. This one is equal to the C change from a 0 to a 1, so we're left with A, B bar. A, B bar. So the function, final function, is equal to C bar plus A, B bar. Okay, that's a 3-variable map. Let's do a 4-variable map. Okay, this one has quite a few more ones, and so again, this is the truth table, and this is the Karnaugh map for that truth table. So let's do some subcubes here. Okay, well, I see an 8 cube here, an 8 covering, 4 and 4. So there's an 8 covering right there. Here is I'll do a different color here. Here's a 4 covering right here to pick up this one. And then here's another 4 covering right here. And then here's a 2 covering right here. This one and this one. Okay, so we have an 8 covering, we have 2 4 coverings, and we have a 2 covering. The 8 covering, 2 variables are going to drop out. Sorry, 3 variables are going to drop out. And if we write that 8 covering, the function for the 8 covering, we see that A and B drop out from here to here. The only one that we have left is C, because D went from a 1 to a 0. So this 8 covering is just equal to C. For the green one here, well, let's just go to the next slide. I have them all. No, I don't. Okay, let's continue on. Sorry. For the green covering, we have A and B. A goes from a 0 to a 1, and B is a 1, so we have B. And C went from a 0 to a 1, and D is a 1, so we have BD. And let's look at the red covering. Here's the red covering right here. So the red covering is A stays a 1, and B goes from a 1 to a 0, so we're left with A. And from here to here, C goes from a 0 to a 1, and D stays at a 1, so we get AD. And then we have the last blue covering here. For the blue covering, right there, that's just a 2 covering, so we look at A and B. It's A bar, B bar, because A and B didn't change. And what changed from here to here? If we look, C went from a 0 to a 1, and D stayed a 0, so we get D bar. So the final function is equal to C plus BD plus AD plus A bar, B bar, D bar. And that's the final answer. Okay, and this one we had an 8 covering. An 8 covering was nice because we dropped out 3 variables. All right, let's do a 5-variable map. Give ourselves a little more of a challenge here. Okay, let's look and see what we got here. Well, we know we got 4 right here. And also we know we got 4 right here. And we know that this whole row is adjacent to this whole row. So these are together. So there's one covering right there between the two maps. Okay, let's look at another covering. Well, we have these two right here. Okay. And we have this one with this one. So this one goes across between maps. Okay, and we have the four corners right here. We have these four corners. We have this one, and this one, and this one, and this one. They're all adjacent. So these four blues are tied together. And then finally, we have this one here that's out there all by himself. He's not adjacent to anything. Okay. So let's write out this function. The black one is equal to, well, we know we went from one map to the next, and we know that E went from a 0 to a 1, so E drops out. So the function of A, B, C, D, E equals this one right here. We know that CD drops out from here to here. E has already dropped out because we went between maps. So we're left with a 1, 0 for AB. So that's AB bar. So that black covering is AB bar. Plus, let's do the blues right here. Let's do the four blues. The four blues, we know that E is going to drop off. And from here to here, we have A went from a 0 to a 1, the same here. A went from a 0 to a 1, and B was a 0. So we know we're going to have B bar. And C and D didn't change all the way across. So we have C bar, D bar. Okay, let's do the red one here. For the red covering, we've got we know we have A changed from 0 to 1, so we got B bar. And then we got C, D bar, because C and D didn't change. C, D bar. And then because we're only in this map, we're not in that map too, E is a 1, so we picked up E. Okay, so that's the red one. So now let's do the green one. It's plus. Okay. We know that the E is going to drop out because we went between the two maps. And what we're left with is A bar B, C bar D. A bar D, C bar. Oh, I'm sorry. A bar B. So A bar B and C bar D. And then for our last one, we have just this single cube down here, and it's equal to A is a 0, B is a 0, C is a 1, D is a 1, and E is a 0. So we get A bar, B bar, C, D, E bar, because E is a 0, E bar. Okay, that's an example 8-variable map. And sometimes it's not too obvious to see what's adjacent, but basically it's the same as 2 4-variable maps. And anytime you have common ones between the two maps, you can use those to reduce the variable that's common between the two maps. And in this case, it was E. Okay, now we're going to introduce the concept of don't cares. And what do we mean by don't cares? Well, if you look at a function, for instance, this function right here, what we're saying is for this logic network, we have 4 inputs, W, X, Y, Z, and we have 1 output. Okay, we have W, X, Y, Z as the inputs and 1 output. And what we're saying, because we're the designers of this circuit, that these combinations will never occur on these inputs. In other words, we'll never get a 1 0 1 0, 1 0 1 1, all the way down to 1 1 1 1. Those will not appear on the inputs at all. So if they don't appear, what we can do is use them as what we call don't cares, or Ds. And we'll talk about that. Let's look at the Karnaugh map here. If we look at everything below the 9, again, because we say that W, X, Y, Z in our design, anything above 9, 10 through 15 is not going to occur. So we can use something called a don't care. And what the don't care says, if you want to use it as a 1, you can. You don't have to, but you can use it as a 1. And if you do use it as a 1, it's going to help you minimize and get a better solution. Okay? So we're going to minimize this function for both the SOP and the POS. Okay? So let's do the ones first. Okay, let's look at, we've got these 2 1s right here, and we've got 2 don't cares. Well, we're going to use these don't cares as a 1. So we're going to say, well, we don't care, so they're going to be a 1. How about the other ones here? Oh, they're going to be zeros. Okay, or we don't care. Okay, here's another 4 up here on the top, and we're going to use this don't care as a 1 because it's not going to occur. So we can say it's a 1. It's called a don't care. So we have this 8 cube because we have 4 in the top and 4 in the bottom, and we were able to build that 8 cube because we used the don't cares of the function. Okay, so what's that going to be? So we can see the WX changes all the way across, and what changes from here to here? What changes from here to here is a Y, so what we're left is Z bar. Z bar. Let's look at the POS. Let's look at the POS version. Okay, so in the POS version, we're mapping the zeros of the function, and we have a 0 here, 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 and here. But we have don't cares in here too. So we can use these don't cares as zeros. Like we said, we could use them as a 0 or a 1 because we don't care, because we're not going to ever have that combination. So we can circle all 8 of these. And again, what does that equal to? Well, the covering eliminates WX because they both change from here to here. What doesn't change? Well, if we go from here to here, what doesn't change is Z. And Z is a 1. And when you're mapping these zeros, when there's a 1, you complement the function. So again, these 2 are identical. And that's because we got this minimal solution because we used don't cares. Okay, let's do another little more complex function. This is the first time we've introduced a function where we have 4 inputs and we have more than 1 output. In fact, we have 10 outputs. We have output 0, output 1, output 2, output 3, output 4, output 5, 6, 7, 8, 9. So there's 10 outputs that are coming out of this binary to decimal converter. And again, we're saying that these the input numbers A, B, C, and D will only run through these 10 numbers, 0 through 1, 0, 0, 1. These down here will never occur. These will never occur. So that since they never occur, we can make them all Ds, or don't cares, in our map. All right, let's look at what the Karnaugh maps look like for this particular function. Now, you can see that we have 8 outputs, 0 through 9. Okay, if we have, which is I'm sorry, we have 10 outputs, 0 through 9. So we're going to have 10 unique Karnaugh maps. We're going to have a map called 0. We're going to have a map called 1. We're going to have a map called 2. We're going to have a map called 3. We're going to have a map called 4. We're going to have a map called 5, 6, 7, 8, 9, as we see down here, 6, 7, 8, 9. Okay? Again, there's like 10 outputs, and so we have 10 output functions, 0 through 9. Here's a mapping for the first function, and we can see that there is no better covering than a 1 covering. And so the function is equal to a bar, b bar, c bar, d bar. Okay, the second one, the same thing. We can't take advantage of any don't cares, and so the output's going to be a bar, b bar, c bar, d. That's this one here. And as we go down the line here, this is 2. 2, we actually did get to take advantage of a don't care, and function 2 came out to be b bar, c, d bar. Okay, how about function 3? Well, we got to use a don't care. So that don't care gave us this subcube, which reduced to this product term, b bar, c, d. Function 4 reduced to b, c bar, d bar. Function 5, we got to use the don't care and reduced to b, c bar, d. A little adjustment there. Okay, output function 6 reduced to b, c, d bar, 7 b, c, d with this covering, 9 a, d, because we have a 4 covering, and then actually 8 we have a 4 covering, and 9 we have a 4 covering, and reduced to a, d bar, and a, d. Okay, so here's the final output. Here's the final function, and you can see that we have the 4 inputs. We have the logic associated with each of the outputs. 0 is going to be a, b bar, c, c bar, d bar, and then on down the line, 9 is going to be, 9 is going to be a, d. So we have 10 outputs, and when any one of these, for instance, when 0, 0, 0, 0 appears on the input, only this one's going to be true, which will be a 1. Okay? And whenever we have a 9 here, which will be a 1, 0, 0, 1 on the input, that's going to be a 9. The 9 will become true. All the rest will become false. So you can put the binary combination of 0 through 9, and each of these will individually come up, telling you whether you have a 0 all the way down to a 9. Okay, so in summary, in this video we demonstrated different ways to minimize Boolean expressions by grouping ones of the functions so that a minimal expression can be obtained. We also did a product of sums mapping where we mapped the zeros, and we showed how you could map zeros and create a sum of products form. I'm sorry, map the zero and form a product of sums form. The ones, you get the sum of products. Okay, so then we showed Boolean reduction techniques for 3, 4, and 5 variable maps. We demonstrated those. We introduced the concept of don't cares, and these don't cares really help you a lot. And we'll see that when we get into synchronous sequential machines for logic designs, and how good they are for reducing the number of gates that you have in a particular implementation. They help you immensely in creating a minimal design. And then we designed a Boolean circuit with multiple outputs utilizing don't cares to create a minimal circuit. So instead of having 4 inputs or 5 inputs or 2 inputs and 1 output, for that case we had 10 outputs. So what that shows is you don't have to have a single output. You can have as many outputs as you want in your design. and the truth table will represent that accordingly. Okay? All right, that's it for Karnaugh Maps, Chapter 3, Part 3. Well, that's the end of Part 3, Karnaugh Maps. And I hope you enjoyed the video. Please watch the next video that's going to be coming up shortly. It's going to be on logic gates. I hope you enjoyed it. Thanks for watching.